Okay, hello everyone. My name is Masoud Shirkhorshidi. I'm a PhD student at New Jersey Institute of Technology, working on my PhD under supervision of Dr. Adams and Dr. Bandel. My today presentation is about the corrosion performance of ultra-high performance concrete in uncracked and cracked beams. It's a student's perspective. This is a part of a bigger project funded by New Jersey New Jersey Department of Transportation to investigate the ductile concrete systems and alternative reinforcement to increase the service life of transportation infrastructures. Because this is a student's experience sessions, I'm mostly going to provide an overview of my technical aspect of my project. I'm not going to talk about in depth about the technical aspects and just focus on my experiences of working with UHPC, mostly mixings, castings, and some of the observations I had during the castings and tests. So first, let's start with some introduction and background information about my project. Chlorides can penetrate into concrete and break the passive layer on the rebar and initiate the corrosion. The corrosion products are expansive and they can impose stress on concrete. This stress can cause cracking, and the cracks can propagate and also ease the penetration of chlorides into the concrete and make more corrosion in the concrete. And finally, these cracks can cause spalling of concrete and expose rebar. One of the possible solutions for solving this problem can be use of ductile concrete systems. In this project, we are focusing on three types of ductile concrete systems, which are ultra-high performance concrete, UHPC, engineered cementitious composite, ECC, and hybrid fiber reinforced concrete, or HFRC. And you can see an overview of the tensile behavior of these materials compared to ordinary concrete. As we can all understand why we say ductile concrete system. It's mainly because of the behavior of these materials in tension and flexure. And the other main difference of these materials in tension and flexure, as you can see here at the left, is the cracking behavior of these materials. In ordinary concrete, we usually have a crack in the middle of a specimen, for example, in the flexure that starts and getting bigger and bigger until we have the failure. But in ductile concrete systems, instead, we have multiple microcracks in different places of the specimens. And this can cause a big difference in the corrosion behavior of these materials compared to normal concrete when we are talking about the penetration of the chlorides to cause the corrosion. Also, I have provided a summary of the mechanical properties of these materials, and these materials generally do not spall and retain residual strengths in compression. At this slide, you can see an overview of the mixture designs and constituents of these three different ductile concrete systems. In UHPC, we have binders, including cement and SCMs like silica fume, ground silica, and so on, depending on the mixture design you're using. We have very fine sand, we have water and admixtures like superplasticizers and accelerators in some cases, and steel fibers. In engineered cementitious composites, we have, again, cement and SCMs like fly ash, a large volume of fly ash, very fine sand, and water and some admixtures like water reducers and viscosity modifying agents, and also polymeric fibers. And in hybrid fiber reinforced concrete, that is pretty similar to normal concrete, we have cement and SCMs, depending on the mixture design, and fine and coarse aggregates like the normal concrete, and water and admixtures, and both steel and polymeric fibers. So we are going to test these three materials in corrosion using ASTM G109 test method. This is an accelerated corrosion test. So the test scale is we are going to make concrete beams with 2 layers of rebar. The rebar at the bottoms are catted, and the rebar at the top, it's going to be anode. And we're going to pound these specimens at the top with a salt solution. So the salt penetrates into the concrete and initiate the corrosions at the top rebar. because we want to consider the cracking effect of these materials in the corrosion performance, we are going to test these materials in both uncracked and cracked stages. So we use the flexural loading to create cracks into the beams, and we are going to load these specimens up to 80% of the capacity and monitor the corrosion performance and corrosion behavior of these materials using corrosion current measurements and corrosion potential versus reference electrode. And here is the testing plan of my project. So we have 5 different types of concretes. 3 of them are ductile concrete systems. Also, we have 2 mixes from NJDOT, which are high performance concrete and self-consolidating mix. And also I have 5 different types of rebar in my project that I'm not going to talk about this in this presentation. I'm mostly focused on the UHPC. Okay, so I want to talk about some of my experiences while mixing the UHPC and casting the UHPC in the molds for G109. So a typical mixing procedure for UHPC in a shear mixer is first dry mixing. We add all the solid materials and powders and mix it. And then next step is wet addition, which is addition of water and admixtures. And after we get a paste, we add the fibers and make sure that fibers mix enough to disperse and have a homogeneous mix. And at the end of the mixing procedure, we discharge these materials. So I have a video here for you that shows the stage that kind of is wet mixing after adding water and admixtures to the powder. And if you look at the timer, it's mixing for 9 minutes. And it still looks like completely a powder. I have a funny experience. The first time I mixed UHPC, we did the dry mixing, add all the water or admixtures, and just nothing happened. The powder ate all the water. And it was their first mix. I went back and checked all the calculation and stuff, and it was right. So I started to call someone to talk about this problem, and it was like 10 minutes or 11 minutes, and we have a very big shear mixer. And just one of the undergrads was helping me, said, Masoud, come here, something's changing in the mix, and it's the next like kind of, I just did it in a small Hobart mixer to just show different stages of the mix. So this was going to happen. You see some clumps of UHPC, and you see for this mix like 12.5 minutes. And this is happening pretty fast. Like it's like mixing for 12 minutes and sometime between 12 and 13. It depends to the volume of the mix and type of mixer you're using. These things happens, and like 1 minute later, then you have something completely different to the powder you had in the mixer. So, and here you can see, like a few minutes later, you have this nice paste. And at the end of this mixing, I have stopped the mixer to see how's the viscosity. And this is the stage, kind of you can add the fibers and continue the mixing to disperse fibers completely. At the end of the test, you need to run a flow test to make sure that the UHPC you have mixed, it's kind of in the right situation. So you need to, the flow test is pretty similar to the flow test we run for the mortars. You need to fill up the rings with the materials, and some kind of differences. For example, as you see here, you need to take off all materials and add it on the UHPC because these materials are kind of sticky, specifically if you have high volume of silica fume in your mixer. And you need to add the materials and let it rest for some time, like 1 or 2 minutes, and then measure the flow test. So here I just, I'm adding the materials. I didn't wait that much. I just wanted to show how is the running the flow test, and I just, pretty quick, just measured the flow to just show you an overview of the flow test and how much is that. I think for now it should be something around 7.5, 8. Yep. And this is an actual flow test I did on the UHPC with fibers in one of my big castings. The flow test should be approximately something between 8 to 9 inches for these materials to make sure that we have the enough flow and also we don't have the sinking of the fibers in the mix. And here, it's one of my castings in G109 beams. UHPC is really unique material to work with. Specifically, we are using this kind of tools in the lab, like scoops, and you need to clean the mixer yourself because, as I said, these are sticky materials, and it takes a lot of time for you to clean all this stuff. And the other interesting thing that was my observation working with UHPC is the difference of finishing the surface, because for normal concrete, you just take off all extra materials, let it set for some time for bleeding, and just finish it. But if you do the same for UHPC, probably you cannot finish it because these materials get relatively fast, get hard at the surface. Not completely hard, but it's hard enough you cannot get a nice finish. So it's better to do it as soon as possible. But after demolding, we got a very nice specimen. So you barely can find any defects or air bubbles or anything at any side of the specimens. And also we got a nice finish at the top too. Okay, let's talk about some of the observations and results I got working with UHPC. So the picture you're looking at is kind of a view of at the top of the dams that I pounded the specimens. The specimen, it's 11 inches long and the dams are 6 inches long. So, and you're looking at the top of the dam. So basically the crack you see is kind of in the middle of the specimen. And this is one of the cracked specimens for one of the NJ-DOT mixes. It's a high performance concrete with 8,000 PSI strengths. And we just loaded it to up to 80% of the capacity. You can see a big crack kind of in the middle of it. The crack is 0.25 millimeters. And the next slide shows the same view of the UHPC. And the interesting thing is that we loaded the UHPC beams up to 80% and nothing happened at it with the eyes. So we continued loading until we get some kind of cracks. We continue loading up to 90%, sometimes to 95% to see some kind of cracks that we can see with the eye. And the main difference, as you can see, is the cracking behavior. And we discussed it first, that we have micro-cracking behavior instead of one big crack in the middle. And here you can see that it's after a few months of pounding with salt solution. So you can see some salt in the cracks. But all cracks are less than 0.1 millimeters. And that's one of the differences with these materials and normal concrete in corrosion. These cracks can be easily blocked with the salts and some of the corrosion products at the various stage of corrosion happening. And I have a few curves of the results so far. It's going to be 1 year soon. The blue line shows a threshold for the corrosion current, and the red line are the measurements for the UHPC. So for now, everything is 0. As soon as you see some kind of corrosion, the red line jumps up and passes the threshold level. It means that you have some kind of electrochemical reaction between anode and cathode. It potentially can be corrosion. And it's too soon for these materials to see some kind of corrosion, probably taking years. And also, I have some specimen, for example, UHPC and epoxy coated rebar, probably takes 10 years. To see some kind of corrosion, if you see some. And this is for cracked ones. I did measurements more frequently compared to the uncracked ones, specifically at the very first stage of a specimen. I didn't know that it's not going to happen that early. So, and at the very end slide, I have a picture, again, same view of the top of the dams for 2 uncracked specimens. The reason I put this picture is here is because of the rust you can see on the top of the specimens. If someone is unfamiliar with these materials and see this, surface on the top of concrete, probably they think we have some corrosion and these specimens are not in good condition, but it's not like that. It's just very top surface of the steel fibers we have in the UHPC, and it has no effect on the corrosion performance or other things in the UHPC. I read in the literature that sometimes they can have even positive effect on the corrosion performance of the UHPC because of sacrificial anodes that we have with these steel fibers. And as the future work in this project, we need to continue measuring response throughout wetting and drying cycles. We do wetting and drying cycles each week. So 1 week of drying and 1 week of ponding. And also chloride profiling of a specimen. At the end of a specimen, we need to make powder on different depths of concrete and see how much chlorides we have each depth. And also we have other durability testing on this ductile concrete system like freestyle salt scaling, drying shrinkage that we casted the specimens and we are just measuring the results for these tests.